Hey everyone, today we're going to be talking about domain and range of a function. Recall that by definition, a function is a rule which takes elements from a set A and assigns them to elements in a set B. And it looks something like this. We're going to call A the set of inputs, which is called our domain, and B the set of outputs is called our range. So you can think of A as a set of everything that you can give to a function that the function can handle, and the set of B is basically the reach of the function. What are all the values that the function f can actually reach? Usually calculating the domain of a function is pretty easy because the only thing that you have to do is rule out certain things. When you're looking at a real function, the only things that you cannot do are divide by 0 and take square roots of negative numbers. Basically, if you can rule out all situations in a function where this happens, you found the domain. The range is a little bit trickier because you generally have to read off values from a graph, but we'll talk about that in more detail later. My favorite way of describing a function is with a vending machine. And I think this is the best way for me to explain the concept of domain and range. So let f be the function which takes codes from this vending machine and outputs the corresponding food item. The way I've labeled this vending machine, I have rows A, B, and C, and I have columns 1, 2, and 3. So basically, any one of those codes will actually output a food item for me. So I can say with confidence that the domain of this function will be the set of codes A1, A2, A3, B1, B2, B3, and C1, C2, and C3. Because these and these alone are the codes that look like they correspond to slots in the vending machine. But I still have this keypad on the right here, which allows more codes than I actually have slots for. So when I'm trying to describe the domain, I'm not trying to see every possible code I can possibly enter into this keypad. I'm only trying to see which codes I can enter that the function knows how to handle. Since I don't have slots for A4, D1, or B0, for example, the function does not know how to handle these codes. So even though I can type those in, if I tried to, I would probably get back an error message. So A4, D1, and B0, and etc. are codes that are not in the domain of this function. When trying to figure out the range, I just look at all possible food items that are available. So I can go ahead and list this out because I've got a range of blue, orange, purple, green, and pink. Now, this vending machine certainly doesn't have all possible food items in existence. It only has ones that have been given to this particular machine. That's the idea of range, is that even though there are foods that could be put into a vending machine, this particular function, or vending machine, only allows these 5 options. So while red, yellow, and gray food items might exist, they are not in this vending machine and therefore not in the range of this function. Naturally, we'll go into some more mathematical examples, but this is the main idea of domain and range. What codes does my function know how to handle, and what are the possible food items I can get? Let's look at some actual examples. What we're going to do is we're going to find the domain and range of the given functions. For starters, we'll look at the function f of x equals to 2 times x squared plus 3 times x minus 1. So with the vending machine, we looked at codes that the machine could not handle. So in this situation, we're going to look for possible x values this function might not be able to handle. So is there any number that we can't input into this function? In other words, are we going to break any math rules, like dividing by 0 or taking the square root of a negative number? In this particular example, the answer is no, because the inputs are either squared or multiplied by 3, and it turns out that there's no real number that you can't take its square, and there's no real number that you can't multiply by 3. So it turns out the domain of this function is all real numbers, which is denoted by the interval -infinity to infinity. This might not feel like the most enlightening example out there, but again, the idea of domain is looking for things that your function cannot handle. In our next example, let g of x equal to 1 over x, and then we ask, is there any number that g of x cannot handle? We notice that our variable x is showing up in the denominator. This means that we are at risk of dividing by 0. So the point is to avoid all possible x values that force the denominator to equal 0. Turns out, if x is equal to 0 itself, then we are dividing by 0, and this is the only number in this particular context that g of x cannot handle. So all I need to do is write this out in interval notation and then skip over the number 0. This will look like the open interval from -infinity to 0 unioned with 0 to infinity. Just to reiterate, the only number that forces the denominator to be equal to 0 is 0 itself. So I rule that out, because 0 cannot be in the domain of this function, but every other non-zero number is okay. In these next few examples, we'll do the same thing of finding the domain of the following functions, and we'll put our answers in interval notation. For our first function, consider f of x is equal to 1 plus the square root of x minus 2. So in our last example, the problem that we encountered was division by 0. However, the problem that we're going to encounter here is taking the square root of a negative number. And I know that this is a problem because my variable x is within a radical sign. So, since I can't encounter that problem, to find my domain of this function, I need to figure out which values of x keep my quantity underneath the radical 0 or positive. And the way to do that is to set up the inequality x minus 2 is greater than or equal to 0. And then once I solve for x in this inequality, I get an answer of x is greater than or equal to 2. So normally, finding the domain of a function is sort of a ruling out process. We need to figure out which values of x are allowed and are not allowed. I know right now that since I am at risk of taking square roots of negative numbers, I need to ensure my x values are always positive or equal to 0. So by setting up this inequality, I find precisely those x values. Since I don't have any other variables showing up in this function, this is all I need to do. Now that I have landed at the inequality x is greater than or equal to 2, this tells me exactly what my domain should be. Writing this in interval notation, I get the half-closed interval from 2 to infinity. The strategy that's in place here is every time I see a variable underneath my radical sign, I take everything underneath the radical and I set it greater than or equal to 0 and then solve for x. Again, every single time that you have a domain problem and you have a square root somewhere with your variable inside the radical, you have to set the inside greater than or equal to 0 and then solve for x in that inequality. For our next example, consider the function g of x is equal to the square root of 4 minus 2x all over x plus 3. So we got two things going on here. We have radicals containing variables, and we have variables in denominators. We're going to take the quantity inside the radical and set it greater than or equal to 0 and help us read off part of our domain that way, but then we have to drop down to the denominator and make sure that we are ruling out all additional x values that don't need to be considered. Namely, the x values that we're ruling out are the ones that can force the denominator to be equal to 0. So first I'm going to set 4 minus 2x greater than or equal to 0, and when I solve for x, I find that x has to be less than or equal to 2 to keep the quantity underneath the radical 0 or positive. Now I'm going to set my denominator equal to 0 and solve for x, and find that x equaling to negative 3 cannot happen because that is going to force the denominator to equal to 0. So, cataloging all my information, I find that x has to simultaneously be less than or equal to 0, and that x cannot be equal to negative 3. Compiling all this into interval notation, I get the open interval from negative infinity to negative 3, union with negative 3 to 2, closed at 2. Notice that this interval is actually the interval from negative infinity to 2, closed at 2. However, I have skipped over the x value negative 3 because I cannot allow that to be in my denominator. Therefore, I found the domain of G. For our next example, let's do one that's a little bit more involved. We're going to define the domain of the following functions and write our answers in interval notation. First, let f of x equal to 2x plus 3 over x squared plus 3x minus 4. Looks like I don't have any square roots happening here, but I do have variables in my denominator. So I conclude that the numerator is pretty much safe, I don't have to work with that, but I have to figure out where the denominator can possibly be equal to 0. So we'll set up the equation x squared plus 3x minus 4 equals to 0, and then solve it. By examination, we notice that x squared plus 3x minus 4 does factor into x plus 4 times x minus 1, and then we find that x equals to negative 4 and x equals to positive 1 would be our solutions. With this information, we know that our domain cannot contain the points x equals negative 4 and x equals 1, so our domain is everything except for those numbers. We write that as the open interval from negative infinity to negative 4, union with negative 4 to negative 1, union with 1 to infinity, because this union of intervals skips over negative 4 and skips over 1. For our last domain, we'll be finding the domain and the range of the function because we'll be given a graph, and we're going to write our answers in interval notation. So let f of x be shown in the graph like so. Recall that with the x and y plane, the x-axis represents our inputs of the function, so our domain, and the y-axis will represent our outputs, so our range. This way, we'll be able to read off all the information we need just by the picture. So like I said, when looking at the domain, we're going to look at which part of the x-axis is covered by the function given. A portion of the number line is surrounded by the blue line, a portion is surrounded by the orange curve, and the last portion is surrounded by the purple curve. Let's look at the blue portion, the leftmost line that's slanted upwards. It looks like the portion of the number line that's covered by this goes from -4 to -2, where I have an open circle over -4 and a closed circle over -2. Next, in regards to the middle orange curve, I see that the portion of the x-axis covered goes from 0 to 1, where I have a closed circle over 0 and an open circle over 1. Last, with the rightmost purple line, I covered the portion of the number line from 2 to 4, where I am closed at 2 and open at 4. Therefore, I can actually just start reading off my domain, and I get the interval open at -4, closed at -2, union with the interval closed at 0 and open at 1, unioned with the interval closed at 2 and open at 4. Again, this is just all portions of the number line covered by the function. When reading off the range, I play the exact kind of game. I'm going to shade in the portions of the number line covered by my functions in regards to the y-axis. So I'll shade in this tall portion here from -2 to +4, where I'm open at -2 and open at 4, and I also get the point -3 sitting by itself. So the way that this would look in interval notation is I would put curly braces around -3 because that's a point by itself, and then I would union that with -2 to +4, where I'm open at -2 and closed at 4. And the open and closed nature is governed by the open and closed circles around those numbers on the y-axis.